work through an example of a series RLC circuit with a alternating current. The resistance is 200 ohms, capacitance 70 microfarads, the inductance 230 millihenries. It is a driving frequency of 60 hertz. The amplitude of the EMF is going to be 36 volts. And we're going to find the impedance, the phase angle, which would tell us the power factor, so cosine of 5 is the power factor, the current amplitude, and then we want to draw a phasor diagram for this circuit. Okay. First thing we want to do to address what the impedance Z is we need to find the capacitive and the inductive reactances. So we are given driving frequency of 60 hertz, and we want to convert that over to the driving angular frequency, because that's what's in the reactances. That's going to be 2 pi times the driving frequency, and that's going to give us 377 radians per second. And we'll try to use consistently, if it is in hertz, means the frequency, and I'll write it out as radians per second for its units when it is an angular frequency. Although, of course, radian is dimensionless, hertz is 1 over a second, so these are identical. But at least that would give you, by looking at the units, some footing to tell whether what I'm talking about is a frequency or an angular frequency. All right, the capacitive reactance is 1 over the driving frequency times the capacitance. Put in values for that. Omega driving, 377 radians per second, and the capacitance 70 microfarads, so that's 70 times 10 to the minus 6 farads. And I remember that I need to inverse that, so it's 1 over, and that works out to be 3 decimal points, 37.9 ohms. The inductive reactance is the driving angular frequency times the inductance. So that's going to give us, again, it's the 377 radians per second. And the inductance was 230 millihenries, so 230 times 10 to the minus 3 henries. And that works out to be 86.7 ohms. The impedance is coming from a combination of the resistance, capacitive reactance, and inductive reactance. It looks like resistance squared plus the difference between inductive and capacitive reactance squared, and then all square root. All of these terms are in ohms, so impedance Z is also going to be in ohms. We plug in values. We have 200 ohms squared plus 86.7 ohms minus 37.9 ohms, quantity squared, all square root. It's going to give us 206 ohms. So just a bit bigger than the actual resistance. both the capacitive reactance and the inductive reactance are frequency dependent, the smallest value that the impedance can take is that the impedance will equal the resistance if that term goes to 0, and then inductive reactance minus capacitive reactance being 0 means you're on resonance. So we can tell that this circuit is not being driven on its resonant frequency, and we can tell that it is an inductive circuit because the inductive reactance is bigger than the capacitive reactance. Alright, so we got the impedance, and calculate the phase angle. Phase angle is the arctangent of inductive reactance minus capacitive reactance all over resistance. So it's going to be arctangent 86.7 ohms minus 37.9 ohms over 200 ohms, and that is plus 13.7 degrees. So that is going to be the phase angle for the EMF leading the current in this series RLC circuit. We'll note as we're going through that phi is greater than 0, so this is an inductive circuit. When the phase angle is negative, it's a capacitive circuit. And when the phase angle is 0, it's a circuit driven on resonance. Okay, so we have the phase angle. The current amplitude comes from our generalization of Ohm's law for alternating current. It's the amplitude of the EMF divided by the impedance. So that current amplitude will be, it's 36 volts over what we just found for the impedance, 206 ohms. So 0.175 or 175 milliamps, 0.175 amps. All right, going into drawing the phasor diagram, I want to collect all the information together that I'm going to put in this phasor diagram. It's going to be a busy one. In general, you could just be asked for a subset of these things to plot in a phasor diagram. But we're going to have the amplitude of the EMF. Those are 36 volts. I want to illustrate that the phase angle is 13.7 degrees. We will have a phasor for the current, which is going to be parallel to the phasor for the voltage across the resistor. Voltage amplitude for the resistor is the current amplitude times 200 ohms, which is the value of the resistance. So that's 35 volts. Voltage amplitude for the capacitor, 0.175 amps, times the capacitive reactance, which we found to be 37.9 ohms. It would be 6.63 volts. And the voltage amplitude for the inductor, same current amplitude, 0.175 amps, and 86.7 ohms. So it'd be 15.2 volts. All right. Now, the amplitude of the EMF from our variable source of EMF is 36 volts. You will observe if I were to naively add all these together, I'm certainly getting something bigger than 36 volts. That is not a problem because these are out of phase with one another. Right? The voltage across the inductor is going to be leading the current, so the voltage across the inductor is out of phase with the voltage across the resistor, and the voltage across the capacitor is going to be lagging behind the current. The current leads the voltage for a capacitor. So we're not adding these three numbers together in a straight sum. They are actually phasors along three different directions in the plane. So from the phasor diagram, we'll see how they add together to give you this amplitude of 36 volts. All right. I'm going to draw my phasor so we're picking values off the vertical axis. And I'm going to pick a moment in time where the current and the voltage across the resistor are both 0. So I include those phasors to the longest of the circuit elements. This will be the voltage for the resistor. So there's its amplitude. I also will have a phasor for the current. These are in different units, so that length is actually sort of arbitrary because that is in amps and everything else is in volts. The voltage across the inductor is going to lead the current, and numerically it's about a little under half as big as that. So there's the voltage across the inductor, V sub L, and there's a phasor for the voltage across the capacitor. This is about 7 volts, so this would be the shorter one. Here's the voltage across the capacitor. We're also going to make a phasor so we can interpret where the EMF lies relative to the current. I'm going to make a phasor for VL minus VC. Okay? And since the voltage amplitude across the inductor is bigger than the voltage amplitude across the capacitor, that's going to point up at this instant in time. So then VR, the voltage amplitude across the resistor, is one leg of a right triangle. And then this phasor for the voltage amplitude across the inductor minus the voltage amplitude across the capacitor. It's another leg of a triangle. And that lets us place the phasor for the EMF relative to the current. So here's the EMF, and the EMF is leading the current by an angle phi. And this is in fact an inductive circuit. VL minus VC is pointing up at this point, and the phase angle is positive. So the behavior of this circuit over time is that all of these arrows are going to keep the same orientation relative to one another. They're all just going to rotate together counterclockwise in the plane. So at this instant in time, if I were to pick off the values to read, the current is 0. The voltage across the resistor is 0. The voltage across the inductor is maximum. The voltage across capacitor is minimum. And the EMF is taking this value projected onto my vertical axis for measuring voltages. Okay? And then as time changes, the EMF is going to start getting bigger. Voltage across the inductor gets, resistor gets bigger, current gets bigger. The voltage across the inductor is going to get smaller. The voltage across the capacitor is going to get smaller as all of these phasors rotate together, keeping the same orientation relative to one another, but they all rotate together in the plane.